Hey everyone, welcome back to the channel. In this video, we will solve the nonlinear equation that is x cubed minus 3x plus 1 that is equals to 0 using the Newton-Raphson method with full clarity, calculations and clean logic all the way to 3 decimal places. So if you ever found Newton-Raphson method a bit tricky, stick around. So we are going to make it super simple and even a little fun. So we have a question that find the real root of an equation x cubed minus 3x plus 1 that is equals to 0, and this is our nonlinear equation. We are going to solve this nonlinear equation with the help of a Newton's Raphson method, uh, and we want to check the accuracy till 3 decimal places, and for that we are going to choose x naught is equals to 0.3. That is our initial guess. So first of all, we are going to extract the function from the statement. So we have a function that f of x is equals to x cube minus 3x plus 1 that is equals to 0. After that, we are going to find out the first derivative. So 3x square minus 3, and make it sure that the first derivative should not be equals to 0. After that, we choose or we use the initial guess that is 0.3, and by using this guess we are going to find out the first iteration. So for that case, first of all, we are going to put this initial guess into our main function, that is x cube minus 3x plus 1. So when we substitute the value, we will get 0.3 raised to cube minus 3 0.3 plus 1, and after solving we will get 0.127. So that is basically the value of a function at x naught. Secondly, we need to put this x naught into our derivative, that is 3x naught square minus 3. So we put it 0.3 into this function, so that is 0.3 raised to square minus 3. So after solving we will get negative of 2.73. Now we are going to substitute f of x naught and f prime of x naught into our first iteration. So for the first iteration, we are using our formula, that is the generic formula of Newton-Raphson method, that is xn minus 1 negative of f of xn minus 1 over f prime of xn minus 1, and in that formula n varies from 1 to 3 up to so on. So for the first iteration, we are going to customize this general formula. So we put n is equals to 1, so it becomes 1, here 0, here we also have 0, and here we also have 0. So we already calculated the f of x naught and f prime of x naught. So these are the two values. We are going to substitute back into the back into the formula of NR method. So x1 that is equals to 0.3 negative of, so we have the value 0.127 divided by negative of 2.73. So after solving, we will get x1 is equals to 0.346520. Now we proceed toward the second iteration. So for the second iteration, we need to customize the formula by putting n is equals to 2 into a generic formula. So our specific or customized formula will become x2 is equals to x1 minus f of x1 over f prime of x1. So we need to substitute the updated approximation result into the function and its derivative. So first of all, we need to find out f of x1 and f prime of x1. So I'm going to separately replace my values. So that should be x cube 1 minus 3x1 plus 1. So we need to substitute here, that is 0.346520, that is equals to 0.346520 raised to cube, negative 3 0.346520 plus 1. So after solving we will get the results 0.002048. Now we substitute back into the first derivative. So it's become 3x1 square minus 3. So it's gonna be 0.346520, that is equals to 3. 0.346520 raised to square minus 3. Now after solving we will get negative, not negative, positive 2.639771. Now we are going to substitute f of x1 and f prime of x1 back into the formula at their respective places. So x2 is equals to x1 is 0.346520, negative 0.002048 divided by 2.639771. So after solving x2 we will get 0.347295. So that is our second approximate result. So if we compare the second value of x2 with x1, so till two decimal places our solution start repeating. So in the question it is mentioned that we need to check the accuracy till three decimal places, so we need to go for more iteration. So if you look here, we have x2 that is 0.34, and if you look at x1, so we have 0.34. So at the third place we have 6 here, and at the third place we have 7 here, so we need to proceed to the third iteration. So for the third iteration we need to customize our formula by putting n is equals to 3 in the general formula. So it's become x3 x2 minus f of x2 over f prime of x2. Now we need to substitute the value, but before substituting the value we need to find out the f of x2 and f prime of x2. So for that we are going to choose our function, major function that is given in the question. So we have x2 cube minus 3x2 plus 1. So we are going to substitute it. We have 0.347295. So we are going to substitute here 0.347295 raised to cube minus 3, 0.347295 plus 1. So after solving we will get 0.4 times 0, and then we have 35, or in other words we can consider it 3.5 into 10 raised to the power negative 5. Then we substitute in the derivative, so it should be 3x2 negative of 3, so that should be 0.347295. So that is equals to 0.347295. We have 3 here. We have, yes, we have a square here and negative of 3. So after solving, we will get the results that negative of 2.63816. So now we are going to substitute this value and this value back into the formula of NR method, that is a customized formula according to the third iteration at their respective places. So we have x3 is equals to x at the place of x2 we have 0.347295 minus we have 0.4 times 0 and then we have 3.5 divided by negative of 2.63816. So after solving we will get 0.347308. Now we are going to comparing the answer of second iteration and the third iteration. So second iteration would be 0.347295 and the third is 0.347308. So if we compare both of these results, so we achieve an accuracy to 3 decimal places because till 3 decimal places our answers start repeating. So we can say that finally that hence the approximate root correct up to 3 decimal places is x is equals to 0.347. And that's it. We just found the root of the equation step by step by using the Newton-Raphson method, and our answer correct up to 3 decimal places is x is equals to 0.347. So if this helped you out, don't forget to like the video, subscribe and drop a comment if you want to see more step by step numerical method solved by hand. So thank you so much for tuning in. Take care.